We are almost done with section 4.6. We did most of 4.6, but we'll finish that up today and work a couple of more example problems over that, and then we'll go through section 4.7 today. And then Monday is supposed to be review day and test next Wednesday, right? Now I'm gonna make an offer to you, right? So we can decide what you want to do, but I have to travel next Tuesday. I have to travel there and back to Washington D.C. in the same day, which means I'm not going to have any. Well, I guess I got plane time to make your test, but I'm worried about being ready for the test on Wednesday. But I can make it. If we postpone the test to that next Monday, that would buy me a little bit of time, but it would mean you'll have an extra section on the test. But that means your third test will have one less section. Know what I mean? So, it's up to you guys. It's really not that big a deal for me to have the test ready by Wednesday. It just means I have to work more over this weekend before I travel, instead of, I would have done it on Tuesday, because that's my day when I don't have classes. But since I don't have that day because of this quick trip that I got to do, then yeah, we could do a show of hands. How many people feel like they'd rather leave it on Wednesday where it was planned, because you've been planning on that? How many people would rather wait till the next Monday? It seems to be unanimous, with maybe a couple of abstainers. Okay, so we'll do the test then on Monday. What's the date?
19th.
Monday the 19th. Okay, so exam will be 10. Oh, that's my wife's birthday. So I gotta move it. No, she'll just have to deal with it. So exam will be 10/19, and right now the syllabus says it covers up through section 4.7, and then there's still more in chapter 4 left after that, I believe. Let me get to the book here. Yeah, there are 10 sections in chapter 4. So I was going to do 8, 9, and 10 on the third exam, but we'll probably go ahead and do section 4.8 and put it on this exam, which deals with interaction. Okay? So there we go. Any questions over the 4.5 and 4.6 stuff that we've done already? No questions?
So, I don't know if you said this or not. Is the review going to be next Wednesday then?
The review will be next Wednesday. That's right. So, and I should have a review sheet for you. If you go looking on the weekend and it's not there yet, then let me know, because I would have forgot. But I'll post it. The one that I used last year should be pretty close, because we're right on sync now with where we were. But we're off a little bit. I'm going faster this semester than I did last semester, so that makes you feel good, right? That means you guys keep up better. Okay, so section 4.6, we've already started it, but it's about confidence intervals and prediction intervals from a multiple regression model. So confidence intervals and prediction intervals from a multiple regression model. Okay? What is the predicted value of y?
Theta 0.
Okay. And I'm going to use, he said beta 0. I'm going to use B0 because we won't know what the betas are, so we'll use estimates. But
okay, so B0 plus B1x plus B2, or X1.
X1.
Plus B2, X2, plus all the way to BNXN, or BKXN.
Yeah, okay. All right? So there's our predicted value. Now, just like in simple linear regression, the predicted value can either be thought of as the predicted mean of all of the values or all of the subjects with this particular combination of x values, or it can be thought of as the predicted value for the next subject that has that combination of predictor variables. Okay? So when it's a mean, we try to remember, and I don't always. We write the mu sub y given x, right? No hat on the y there. So mu sub y given some combination of the x's. Now this is all fairly straightforward for prediction, but now if I'm going to do a prediction interval, we have to know what? To do a confidence interval for this mu, what would I have to form a confidence interval? The standard error of that predicted value, right? So for a mean, we're talking about confidence intervals. I'm just going to say y hat without the mu thing, but y hat for a given x sub 0 underscore. And what is that saying? Right, that's saying the vector of x values. Right? So think of it as a particular row in the x matrix. Because a row, you've got columns are the different x variables. So one row is a combination of values for those x variables. Right? So for a given vector of values, y hat plus or minus, what goes next? A critical value. So t crit, it's going to be a t, just because we have the normality assumption, makes everything be distributed as a t. And what would the degrees of freedom be? Okay, so it's degrees of freedom for error. So I always write that DFE, but that's n minus quantity k plus 1. So that's to look up the t critical value, you're going to need to know its degrees of freedom. Right? And then the standard error of a mean predicted value. Think back to what it was in simple regression. So simple linear regression, the standard error of y hat for a mean. You remember what it was?
SE times the square root.
Okay, SE times the square root. 1 over n.
X sub 0 minus x bar.
X sub 0 minus x bar squared over n minus 1 sx squared, which can also be written as ssxx. Right? Or it could be written as sum of xi minus x bar squared. All three of those mean the same thing. Right? Or they are the same thing. And this thing under the square root we called the what? The distance value. So all of that is referred to as the distance. And it's the distance from what? Not from the predicted value. Well,
From the average?
yeah, from the average. And what do we call the average? the centroid. Right? So when it's a simple linear regression, we have basically an ellipse of points. Right? The centroid is the center of that ellipse. When you have two x variables, you add a third dimension and you get an ellipsoid. Right? An ellipsoid. Looks like a football. As long as it doesn't have weird shape. The center of that football is called the centroid. If you got another x variable, now we're out of dimensions in our brain. We can't picture it, but it's the same idea. It's just the centroid is the mean of all of the x variables. Right? So if you got 5 x variables, it's x sub 1 bar, comma, x sub 2 bar, comma, x sub 3 bar. That's your centroid. And then the y bar on there also. Okay? So same thing here. In a multiple regression model, we're going to have S sub E, and I forgot to say it, but everybody knows what S sub E is, right?
Square root of MSE.
Square root of MSE, right? That's the root mean squared error from the model. So it's going to be the same thing in a multiple regression. It's just root mean squared error. So I'll go ahead and write that here. Root mean squared error. And then square root of the distance value. Now, when it's a simple linear regression, we had a formula for that distance value. We can still get a formula for this distance value, but it's going to be in terms of matrices. It's very complicated if you don't use matrices. So I had this on the board last time. Good. And remember, we had a brief discussion about why the authors put the prime where they put it. And I don't like the fact, but I got to stick with what the book did. But the way the authors say it is, let x sub 0 prime be a row vector which has 1 and then x0, 1, x0, 2, x0, 3, dot, 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 x0, k. Where the first subscript is matching the subscript here. And then the second subscript is the number of that x variable. This is the first x variable, second x variable, third x variable, and so on. Okay? So then, what is the distance value? Okay, so the distance value is x sub 0 prime, this thing, times
the inverse of x prime x times x.
Okay?
Do we still have the 1 over n?
Yes. It's in there. And I'm going to prove that to you here in just seconds.
Oh, sorry, last time
I said that name went, oh God. But you'll be happy to know I did it on paper and I scanned it. And I'm just going to show it. Right? I'm not going to take the time to write it all out. And I'm not going to make you have it in your notes. But I want you to see that, oh, this does work. Right? But, so it has a 1 over n in there. But it's also got all of the cross product terms between all of these x's that make that centroid. When it's simple regression, you only have one x variable, then it's easy. But and then remember we talked about the hat matrix. What was the hat matrix?
well, it's just that. Well, it's x.
Yeah, now the prime shifts, right? Which is what I don't like. The book that I learned it out of didn't have the prime on the vector up here either. So it was a x with no prime was the row vector, and then when you primed it, you got a column vector. So it's the same thing. It's just it's where you like your prime, I guess. So.
Times by x or y.
That's called the hat matrix. And do you remember why we said it's called the hat matrix? You guys don't pay any attention, do you?
Well, because it gives the diagonal elements are the hat values of SAS.
Okay, well, why the word hat?
For the competition, the distance value already predicted.
Yeah, but if I take this thing and I multiply it by y, so we're going to call this h for hat. If I take h times y, what do I get? I get the predicted values. It puts the hat on y. So that's why it's called the hat matrix. I didn't make it up. Some other statistician with a good sense of humor made it up, right? So they call it the hat matrix because when you multiply it by y, it puts the hat on y. Yep.
X prime is not related to the transpose, or is it?
Yeah, this is the same X matrix all the way through here. And so this is my X matrix, and then this is the transpose of that X matrix.
The prime is just another way of saying transpose.
Oh yeah, did I not mention that? I'm so used to doing primes, that's how I learned it in graduate school, but X prime is interchangeable with X transpose. Sorry about that. Right. So, and remember we did that one thing with proc IML and SAS, and they use a little prime symbol, but
So the only difference is versus switch to transpose, but the distance value only does one row, but the x's and
right.
does them all.
Yeah. So let me answer his question, and then I'm going to come back to that.
So you're multiplying it by the y matrix, which is all the known values of y,
Right.
and then you get the predicted values for those same values of y using your x, using what you found in you get an x.
Yeah, well, remember that y hat is x times b. Right? That's this thing that we wrote right here. Right? Y hat is X matrix times the B matrix. Right? Well, B's are a column vector, so you get this sum. It all works out. So this is my predicted values. But this is that. Right? That's the beta hat, or the B vector, is all of this. When we did that matrix algebra solution to the linear regression model, so this is all the vector B. So now you can see, well, if I call this first part of it H, then I take H times Y, and I get Y hat. Okay? Kent still had the biggest scowl on his face, but he started nodding, so I took it.
Sorry, yeah.
Okay? Now, you said, what did you say? Something about diagonals.
I said something about the only difference between the hat matrix and distance value is the distance value is the row of x's, whenever the hat matrix uses all the x's.
Right, so what's going to happen, if I take this X matrix and I break it into its individual rows, and I do them one at a time, these form the diagonals of the full hat matrix. The off-diagonal elements are when you have one row of the X matrix and then crossed with a different column. So it's only the diagonal that uses the same row with its transpose as the column, right? And that's what gives you the distance values. The other things in the hat matrix are of interest, but not really in this class. They give covariances and things like that, right? But it's the variances that we want, which are the diagonals of this X prime X matrix, X prime X inverse matrix. And then with the multiplication by the particular row of the X matrix, it gives us the distance values. Right? So standard errors are part of this distance plus the the distance that it is from the center of the centroid. All right, so now here's the proof that I promised you. Now, unfortunately, it looked a lot better. Well, it doesn't look as bad here. On the screen, it looks pretty faded out. It's hard to see my handwriting, but that looks okay. Do you have a question before I get going?
So, if you just give us like the x prime x inverse matrix, the variances are the diagonals of that. So, the first one would be
the variance of beta 0 or b 0. Yeah. And so remember we talked about confidence intervals and hypothesis tests for the parameters. So for the beta 0, beta 1, and all those, their variances are on the diagonal of this matrix. Right?
And the covariances are the other ones?
Yeah, the covariances are the off diagonals. That's exactly right. Right? So recall, in simple linear regression, meaning there's only one x variable, we made our x matrix, and then we found this. Remember, we spent a whole day doing this. We took x prime, x inverse, and we had this scalar multiple out front, and then we switched places, and, did the whole inverse thing, right? And that's what it was. If you don't trust me, you can look back in your notes. I'm not going to redrive that. But all I did here was distribute this scalar back into there. So no problem yet. So if we define the vector x sub 0 prime to be the first row, or in this case I did use the first row, but it doesn't have to be any particular row, but a row from the x matrix. Remember, the x matrix has a column of 1s and then a column of values for the x variable. So this is just one of those values. Got it? And then, let me scroll down. If I pre-multiply x prime x inverse by that column or that row vector, and then I post-multiply by the column vector, this is what happens when you don't plan ahead in how much space you're using. I had to say, okay, here's an arrow. This thing is setting up there, right? So it's just matrix multiplication. So let's do the first one first. I'm going to take this thing. Picture this sitting out front here, and that first column of the x prime x inverse matrix. So I have to scroll back up so we can see it. So if I take this times that matrix, right? So I go 1 times this whole thing plus x sub 0, 1 times this whole thing. So that's these two terms. Got it? And then I move to the next column, and I have this same thing, 1 times that, which is here, plus x sub 0, 1 times this. So x sub 0, 1 over that thing. Okay? That's pretty easy. Now, I'm going to finish the multiplication and multiply by this. So what I have now is a 1 row, 2 columns times 1 column. Is that right? Yeah, I wrote them here. So the first one was a 1 by 2 and then a 2 by 2. So I end up with a 1 by 2. So then I have a 1 by 2 times a 2 by 1. So my answer is going to be 1 by 1. A scalar. I'm going to get a number back. Right? So now let's do it. I take this whole big long thing times 1. And that's this. Got it? And then I take this whole big thing times x 0, 1. Well, that gives me, this one's negative, so negative x 0, 1 times x bar plus x 0, 1 squared, because there's an x 0, 1 and an x 0, 1. Right? Got it? So it's algebraically getting a little bit messy, but it's just pretty simple matrix multiplication. Now, from here I got stumped for a while, and I thought, okay, now what do I got to do? But then I remembered something that one of my professors back at Emporia State said to me. You know, if you can just learn to multiply by 1 and add 0 to stuff, you can prove a lot of things. So, okay, let's see what I can do with that. So, first thing I did, I noticed this is a common denominator, right? So, erase this plus sign, make that line go all the way across, and put one of those on the bottom. And I've combined over the common denominator. Then I add 0. And I add 0 in the form of a negative x bar squared and a positive x bar squared. So I've just added 0 to the expression. No big deal. And then I've also combined other like terms. So I've got a negative x01 times x bar and another negative x01 times x bar. So that gives me a negative 2 of those. Now why did I choose x bar? Because what does this look like? What is that? That's the computational form of SSXX, which is what this is. So these two things can cancel, right? I'm left with 1 over n. And then looking at, so that takes care of this piece of it. Take care of this piece, what does that look like? Something squared minus 2 times their product plus something squared. This is the FOIL method, right? This is intermediate algebra. You learned this in 7th grade, right? If I factor that, it factors into this, right? If you FOIL this back out, you get what's on top there. So having the plus x bar squared completed the square. They call that completing the square, right? And then it gave me the term I needed over here as well, right? So what I end up with, these cancel. I have 1 over n plus x sub 0 minus x bar quantity squared over SSXX, which is exactly what you told me a minute ago was the distance value. You don't have near the look on your faces like I was hoping for. I thought you would, that's the coolest thing I've ever seen. And you're all like, statistical theory. This is what it's all about. Right? The algebra gets horribly messy when you go to more than simple linear regression, and so we don't track it through, but you can prove with matrix algebra that it will always give you the distance from a particular combination of x values, the distance from the centroid of the cloud of points. Right? So it's a matrix theory proof of that. But here's, in the simple case, you can show it algebraically, so we do it there, and then we do what I call hand waving, and it works for everything else too. Right? Okay? So, to get prediction intervals, this is this, not this, it's under here apparently. This is a confidence interval. So the only thing we have left to do in section 4.6 is how do we change this to give us a prediction interval instead of a confidence interval? You just add 1 under the... Right? So prediction interval. So an individual prediction interval is exactly the same but it's 1 plus the distance value. And remember why the 1 is there. It's 1 because I'm adding the variability of the residuals to the variability of a mean. So it's additional variability around a mean. Okay? Now, you've already been asked on the homework to do some of these automatically with SAS. How do you get confidence intervals and prediction intervals for predicted values in SAS? In your model statement, in a proc reg, you'll say model y equal, then you'll list out the x variables, however many you got, then you'll say slash CLI and CLM. And if you put these, you don't have to put the P, but the P is for predicted values. So give me predicted values and then give me confidence limits on those.
So if we do the P, I guess maybe.
If you do P without these, then it just gives you the predicted value but no interval around it.
So you P equals whatever predicted value you want there.
What's that?
You just put P equals whatever predicted value you want.
No, if you want to change to like 99% interval, it's not P, it's alpha. You say alpha equal 0.01 if you want 99% confidence interval. The default is alpha equal 0.05, so if you don't put anything, you'll get 95% intervals, which most of the time that's what you want.
So then,
Okay.
is that a capital P or a...
It doesn't matter. SAS does not ever get picky about capitalization. Unless, well, I shouldn't say ever. If the value of a variable, in quotes, a character string variable, then a lowercase and uppercase are distinguished. But in terms of the syntax, it doesn't care.
I just want to make sure we. Never mind, I figured out the distance value.
Okay?
And do you have that on the second line from procreg or a space after procreg?
Well, let me just show you. If I go into a SAS program, I guess I need to turn this back on. Let's see if I have the Da Vinci data. So I need to run the first few lines to get the data set loaded. Check my log window to see that it did it. It said, it read there are 248 observations with 13 variables. So now let's run a proc reg. Looks like I was doing some other stuff last time about making sure we had all the same observations, right? So I had this data project 1. Yep, that worked. And so we ran this model that had hand, wingspan, and kneeling all in the same model. So it's a multiple regression model. And down here, I'm going to have that same, I need to add hand to this, but I have the CLB. Oh, that's not what I wanted. Clear down here. This is it. So this batch of code gives me a multiple regression model with all three variables. Then it has the CLB. What does that one do? So this option, it says /CLB. No, it's confidence limits on the B's, which are the parameter estimates. So on the slopes for each of the X variables. Right? And then XPX gives me XP for prime, so X prime X matrix.
X transpose X matrix.
Yep. And then the I is the inverse of that. Right? Now, if I had written SAS, I would have made that be XPXI instead of just I. Because I, there's another option for influence statistics And the I always think is short for influence, so I try it and then I don't get it, and I have to. And then I have P for predicted, CLM, CLI. All right? And then I've asked for an output data set, which right now I have commented out, but I'll uncomment it before I run it, that this creates a data set called PRED that has P equal Y hat, which you're just giving it names, but these are keywords. Let me uncomment it so that it'll turn things blue. So P for predicted value, I want to name it Y hat. And then LCLM, what's LCLM? Lower confidence limit on the mean. And I'm just using the same name both times. You didn't have to, but and then upper limit on the mean, lower limit on the individual predicted value, upper limit on the individual predicted value. Now I don't understand why those didn't turn blue. Seems like they should have, like these did, but so I'm going to run that, and then we're going to have a whole bunch of stuff to look at. And actually, I'm going to turn off the ODS graphics so I don't have a bunch of extra stuff that I don't care about right now. I have found, and you've probably experienced this too, that if you don't turn off the ODS graphics, it runs real slow. It's like you hit run and then you go get a cup of coffee and you come back and it's finishing up, right? If you turn it off, then it seems to save a lot of the internal memory or something, so it runs a whole lot faster. But it's still not instantaneous. But okay, now I'm just going to go clear to the top of this. So the first part of the output, it says model cross products. That's my X prime X matrix. And remember, it has an extra row for my Y variable height and an extra column. So it says X prime X and then X prime Y and then Y prime Y. So this single scalar is Y prime Y. And what would Y prime Y be? If you take the Y vector,
The sum
sum of squares of the Y's. So this is the total sum of squares, but it's uncorrected sum of squares. Right. Actually, I don't know if it's... Technically, Y prime Y should be uncorrected sum of squares, but SAS may... We'll compare that number down here.
That's total sum of squares, by the way?
Yes,
Right.
total sum of squares. So then if I scroll down, I get the X prime X inverse matrix. And again, the bottom row and the rightmost column are not part of the X prime X inverse matrix. So the diagonals that we're interested in are down to there. Right? Now, yeah, this answers the question. Look at the corrected total sum of squares for Y. 4135, but up there on that other, it was like in the millions or something. So that is uncorrected, right? It's not mean corrected. Do you remember what that corrected refers to?
It's got something to do with the R squared going down.
No, that's something different. Corrected total sum of squares just means it's yi minus y bar, quantity squared. Sum those up. Whereas uncorrected is just yi times yi, sum those up, without subtracting the mean off first. So the corrected is referring to mean corrected. Right. Okay, so we've already done the exercise of looking at the parameter estimates and the standard errors of those parameter estimates and comparing these to the diagonals of that X prime X matrix, right? And remember, they come off of there, right? The standard errors are root mean squared error times those diagonals. Actually, it's mean squared error times the diagonal, square root of the whole thing. Right? Now, I asked for the confidence limits on the mean, confidence limit on predicted values. So let's go look at those. And this is the standard output from doing it, but I also saved it as a data set. So, oh, this is a big data set, isn't it? Did I not do a proc print of it? I thought I did. No variables in that data set, so I had a syntax error. Don't you love SAS? Those are all warnings, but I have a syntax error expecting one of the following. So it didn't turn those blue because they weren't right. So you see what it's pointing at? It's saying that line that you had, output out equal pred, LCLI equal, and it's saying, hey, that's not valid. So I need UCL mean we got, and then just UCL with no I on the end of it. So that's the nice thing about SAS. If you have syntax errors, at least put some kind of a message in your log window about it. Sometimes they're easy to interpret and sometimes they're not. Particularly if you forget to put a semicolon at the end of a line, the syntax error you get sometimes just seems completely unrelated to that. And so, but this one was helpful. So I'll go in and fix that. Just LCI with no I and UCL with no I, and I'll rerun it. Oh, darn it. I want to add something to that. I not only want the confidence limits, I want their standard errors, because that's what you get from the HAP matrix, right? The distance value. So STDI, did that turn blue? Yeah. Okay, so that's the standard error for individual. And standard error for a mean, I don't think it's M. Nope. Can't remember what it's called, so I'm going to put it, I'm going to have it give me the error message that'll say what it's expecting. So the error message says STDI, STDP. See, who wrote this? P for predicted value. But I'm going to call it STDM so I don't have to remember that. So I can name it whatever I want, but they're going to name it that. So let me clear the output viewer. And run that. Okay, so let's duplicate this with that top row. The top row has a height of 61.5, and then it has wingspan, so I'll call that x1 equal wingspan is 58. Kneeling is 46. 6.75. So this vector is then 1, 58, 46, and 6.75. X prime sub 0, and I'm going to call it 0, 1 for the first. But the sub 0 indicates it's a particular value of x. So that's the notation that our book uses, right? So now if I want the predicted value, so on a test, if I say, give the predicted value, predicted height for somebody that has a wingspan of 58 inches, a kneeling height of 46 inches, and a hand length of 6.75 inches. Then you just take these three values, you plug it into your regression equation, and you got it. You don't have to do any matrix multiplication or anything like that. You just plug them in, right? But if I want to duplicate the standard error, standard error of the mean, so this column, that value, 0.20761. I take this times the x prime x inverse matrix times the transpose of this, right? So I get the diagonal of the hat matrix. Yeah, I started to go up and show that matrix. I don't want to get bogged down into actually multiplying this out. The thing that you can get out of SAS, which I should have put on here, is H equal. So H is SAS's shorthand for the hat matrix, or the hat diagonal values. So then that gives you 0.02942. Now how do I use that value to reproduce the standard error of the mean? Okay, multiply it by the root MSE. The hat value is the thing that's underneath the square root, right? That's the distance value. So I need to take the square root of that number times the root MSE, and I should get that standard error of the mean. So get your calculators warmed up. I don't know if I can put everything on the screen at one time. This number 307684444 is the sum of squared error. So the mean squared error would be that number divided by what? Degrees of freedom for error would be the sample size minus quantity k plus 1. K is a 3 because I got 3 variables in my model, so k plus 1 is 4, and I think it was 214, but I got to scroll up to remember for sure. But weren't there 214 observations in this data?
Error.
Yeah. So there it is. Error is 210. So as long as we're up here, there it is. There is the mean squared error. So the MSE is 1.46516. So if you take the root MSE times the square root of the hat value, that's the square root of 1.46516 times the square root of, I got to scroll back down to see that hat value,
2.02942.
right there, 0.02942. So what do you get when you multiply that all out? .207617 something else? Okay? That number. right? All right, any questions about that? To get the standard error for an individual predicted value, which we've called STDI up there, what's the only thing you change? This becomes 1.029 whatever. You add 1 to the thing under the you add 1 to the distance value. Okay? All right, so that's it for predicted values and prediction intervals. Any questions on any of that? All right, let's go to section 4.7, which is quadratic models. So I'll start without the projector on and get the notation out of the way, and then we'll start looking at some SAS programs, or SAS output, really. So if you have data that is curved, then you're violating one of the assumptions of linear regression, right? That things should be linear. But let's say I have data that looks something like that, right? You might think, well, I could fit if I'm not restricted to a model that has to be a straight line, I could maybe fit a curve to that. That would fit the data very well. So this section is all about quadratic models, which is a part of the general polynomial models. Right? A linear model is a polynomial model, a line, right? A parabola is a quadratic model, but you could get a cubic, right, by adding a x cubed term into it. So the model that will fit I'm going to put the hat on the y so I don't have to mess with the error term, but it's beta 0 plus beta 1 x, and I'm not going to have a subscript on x for now because we're only going to deal with one x for right now. We'll add some others in a while, but then plus beta 2 x squared. So the book has a whole series of pictures that talks about what shapes you might see that lead you to think, oh, I might try a quadratic model to this. But just really anything that's got curvature. So you might see a good share of the parabola like this one, or you might see just a small piece of it. But you notice, well, there's definitely curvature in that. And it might curve this way. It might come up and really flatten out, something, whatever. You've got the opportunity for a quadratic model for any of these situations. Now, we were talking about intermediate algebra before. Do you remember that the equation of a parabola can be written as ax squared plus bx plus c? This is back when you still liked math, right? Doing parabolas and graphing stuff. That was fun. What does the A tell you? What's that? Okay. Good. It affects how skinny or how fat the curve is, right? Small values make it widen out. Big values make it go real steep. If it's negative, it flips it upside down. If it's positive, it's right side up. right? What about the B? What does it do? What's that? I can't understand you. Placement. It has to do with placement of the vertex. That's right. Right? So you probably remember, I like to look at a different form of it. So if you write in this form, now you talk about shifting the vertex around, right? So the A is the same A as before. But now the H is a horizontal shift. So the most basic parabola is y equal x squared, and that has a vertex at the origin, 0, 0. But if you subtract h off before you square it, it shifts it to the right 8 units. If you add h, it shifts it to the left 8 units, or h units. And then what does C do? Shifts it up and down, right? So now if we multiply this thing out, you get ax squared minus 2ahx plus ah squared plus c. So this is in this form. It's also in this form. So what is my beta 0? That's all of this. None of these have an x in them, so these are all constants. So this is my beta 0. The a squared is my... the a corresponds to beta 2. And the beta 1 is all of this. So that's all beta 1. Right? So the reason I'm showing you all this is because what we're used to in terms of interpreting what these parameter estimates are kind of falls out the window when you do a quadratic model. We're used to thinking beta 1 is the slope for the x variable. And then beta 2 is the slope for the x squared. Wait, something's not right. Well, it turns out that this beta 1 is related to h, so it's a shift parameter. So that beta 1 does not affect the slope of the graph. In fact, if I have a full-blown upside-down parabola, I don't have any slope at all, right? So it's a shift parameter. As beta gets big, this thing moves further, right? What does beta 2 tell us? Well, it's sitting right where A is sitting. How wide or how skinny the parabola is, which, and to say that like a statistician, that's the curvature, right? It's the rate of change of the curve. How fast is the slope changing, right? So it's a rate of change of the rate of change, right? So this one would have a pretty high value for beta 2. Right? It's got a lot of curvature. It would also be a negative beta 2. But one like this would be a much smaller value for beta 2. But the actual magnitude of the numbers don't mean a whole lot to me. I can't look at it and go, oh wow, that's a big beta 2. Right? I can do that with slope. Slope tells, oh, that's a big rate of change because I know something about the x variable and the y variable. But for curvature, it doesn't, I don't know. So I rely much more heavily on the statistical tests for these parameters. Is the quadratic term, that's what we'll call this, the quadratic term, is that statistically significant? Is the linear term statistically significant? But you remember, I'm not asking about slope or how steep the line is. I'm asking about, is there any shift, right? Has this thing been shifted away from the origin when I'm testing that? How much curvature is that? Is it a significant amount of curvature or not? Okay. If this beta 2 parameter gets smaller and smaller and approaches 0, what do you end up with? A linear equation, right? You get a line. It's less and less curvature. It gets flatter and flatter and flatter until finally beta, this term goes to 0, that drops out, and you're back to your old friend, the linear model. Right? Now, I'm not using that term quite right when I say the linear model. And the author makes this point in this chapter because this is when it comes up. This is still called a linear model. Even though it's not the shape of a line. Still referred to as a linear model. And that term is applied to the parameters, not the variables. So is it linear in the parameters? So remember when we did the calculus to derive the least squares estimates, we kind of flipped the role of the parameters and the x variables. And so we took the derivative with respect to beta 1. And we took the derivative. We're doing the same thing here. Look at the parameters, decide if this thing's linear, not the x's. So since each of these since it's a linear combination of betas, and they're all to the first power, it's a linear model. So can you think of a model that would not be called a linear model?
Beta 1 squared.
Okay. If you have beta 0 plus beta 1 squared x, that's not a linear model. It's not linear in the parameters. Now, this model, I would argue, well, this is a linear model because I'll take the beta 1 you give me and I'll square it. I've got a different constant and I've got a linear model. Right? But if I made this beta 1, now I can't do that. Now I have a square on that thing and I can't get rid of it. So this is not a linear model. So a model like beta 1x plus beta 1 over beta 0 plus beta 2 x2. It's not linear in the parameters. Right? So anything where the power isn't 1 or there's quotients or whatever, it's not a linear model. So there's a whole other area of statistics, unfortunately I don't get to teach you guys, called nonlinear regression. We'll actually do a few nonlinear regression models in this class, but we do a clever transformation to make them fit the case of linear models. That's how we deal with it here. But
So if beta 1 plus beta 1 squared x is nonlinear, does that mean that beta 1 cannot equal beta 0? Because if beta 1's all by itself, can beta 0 equal beta 1?
because these two are then linked. Right? If I have beta 0 plus beta 1x, then there's no link between these. There's no constraint here. But this one is constrained so that the slope on the x has to be the square of the intercept. Right? So if I try to play, well, I'm going to call this beta 0, well, then I have to make that the square of that, beta 0.
So beta 0 cannot equal beta 1? Or can they equal beta, or can they equal the same thing and not be related?
No.
No, it's still technically linear though, wouldn't it?
This one has to be the square of this one. Whereas a linear model, there's no constraints.
I meant like on a graph, that would still be a line, would it not?
If I graph this, it would still be a line. But the way I estimate the parameters with the least squares will not work because these are not linear in the parameters. That's the big problem with nonlinear models. This least squares estimation doesn't work. Okay? So, let's take a look at some data that deals with this. And what I did was I wrote a little SAS program that will produce some data that has some desired characteristics for me. So if you look at this top section that I'm just about ready to run, it's called dataset number 1, data 1. And I'm just creating a y variable that is known to be a quadratic function of some x variable. And I'm letting x go from 0 to 2 by 0.1. But then I add some random noise around that. Right? So I've artificially created the data that I know is quadratic. So y is related to x in a quadratic fashion. But I put some random noise around it. Okay? And then I create a variable xsq, which is just x times x. So that's my x squared. The way you'll use that in SAS is you put x and then x squared variable into the model. It will not accept x and then x raised to the power of 2. It doesn't take that. So you have to create a variable that is the square of the x and put it into the model. This forces it to be a linear model because it treats those as different variables. So it puts a beta 1 and a beta 2. So let me run that. So there is a proc print of the data. So the first column here is my x, and I ran it from 0 up to 3 by 0.1, so I got a bunch of values, and then I squared them all, and then I generated the y based on the quadratic equation plus some random noise. So if I run, let's print it first. See what we're looking at. Boy, that's ugly. So I could change the random number seed and get a different graph. It should look similar to that, but you see a point way down here, and then you see a point down here, and without those 2 points, I'm not sure I would visually see curvature in this. I would just see random noise around a line. All right, so just by random chance, I didn't get a great setup, but let's go ahead and run the model, see what happens. So now, you can do this with procreg. You don't have to, but you can have more than one model statement. And the reason you might want to do that is, well, I'm interested in running, different combinations of these variables and seeing which one gives me the best R square. So you just drop them all into one procreg rather than have a whole bunch of different procregs. It works identical. All right, so I'm just going to run that. Now you saw from that graph that the ends seemed to curve a little bit, and the middle part was pretty flat, right? But look at the output. My R square value is 0.855. That's the variability in y that's explained by the x's. Then what are we testing here? Not x is 0, but the parameter on the coefficient of x. Right? So that's a test of beta 1 being 0, and beta 1 in a quadratic model represents shift, right? So where's the vertex of this parabola relative to the origin? Well, it's shifted away from the origin, right? I don't know how much that really helps me interpret the data, but basically to me it says, well, you need to keep the linear term in the model because it is significant. It's explaining a good amount of the variability. Then the x squared term is measuring what? The curvature. And it's saying there is a significant amount of curvature in this data. It's not quite as strong as the linear component, but there is definitely curvature in this data. Okay, now let's look at... I went to the wrong program. Let's look at a different data set. This one does a similar thing. It generates some data, but it's a little bit different shape. Oh, I just remember, I forgot to remember I ran two models. We only looked at one of them. I didn't go back and look at the one that only had the linear term, but we'll do that in a second. Look at this data. This looks really a lot more curved. This one's very clearly is curved data. If I look at the output of the regression,
Sir, I have a question.
yep.
In a curved model like that, the R would be zero, and like the correlation coefficient.
He just asked a great question. He said in a curved model like that, wouldn't the R squared be 0? Because remember what R measures? Linear correlation. But when we go to multiple regression, R squared doesn't have the same interpretation. R squared is the amount of variability that's explained by the model. So it's the sum of squares model divided by the sum of squares total. So it's called the multiple correlation coefficient, R without squaring it. Right? So it's the combined correlation between all of the variables and the Y variable. So you can get a fairly significant R even if perfectly curved. You're not only looking at the linear term. Right? So in this one we get an R square of 0.57, so not near as strong. But look at the X variable and the X squared variable. Both highly significant. If I scroll up, there's a residual plot. Oh, I'm sorry. I started to say, well, wait, that doesn't look right. But that's a residual plot from this model, which only had the linear term in it. So when I fit only the linear term, only the X variable, what do you notice about the p-value? Not significant. Now you're testing the slope. And remember, it was like this. So if you don't allow your model to curve, it's going to fit a horizontal line through there. And this is picking that up. The slope is not different than 0. But when I put the other term in, what happens to that linear term? It becomes highly significant. Because now it's not testing slope anymore. It's testing, is there a shift away from the origin? Yeah, there's a shift. You know, the vertex of that parabola was not down here at the origin. It was up. Right? So now you have to know what you're testing. Right? It's not that we have significant linear slope. It's that we have a shift away from the origin for the vertex of this parabola. Now, we only have time to say one more thing, and that's this residual plot. What is it about this residual plot that tips you off that your model that was a line didn't fit very well? The residuals don't look like a shotgun blast. There's a pattern to them. And in fact, it almost looks like the raw data, right? Because the slope was almost 0 in the raw data, so the horizontal line at 0 is just about, you get the same picture that you get a horizontal line somewhere else. Right? So you get this. If you see curvature in your residual plot, then you have to think, oh, I need to fit a quadratic model. And sometimes you don't see that curvature in the raw data very well because of the noise, and it's not curved that much. But as soon as you look at the residual plot, you go, oh, wow. I've got curvature in my residuals. I'm going to go put an X squared term in the model, see if that improves the fit. All right, we will see you next Monday, I guess.